Hi everyone. Today we'll discuss about equalization, diversity and channel coding. This is the outline of this chapter 4, equalization, diversity and channel coding. And first we'll start with the introduction. Then we'll discuss about the fundamentals of equalization. Then the different types of equalization techniques will be discussed: linear equalizers, non-linear equalizers, and after that the different various algorithms for adaptive equalization will also be discussed. Then the fundamentals of diversity topic will be discussed. Then finally we'll end this chapter with the rake receiver. So the first topic is introduction to this equalization, diversity and channel coding. Mobile communication systems generally requires signal processing techniques which improves the link performance in mobile radio environments. Mobile radio channel is particularly dynamic due to multipath fading and Doppler spread. These effects have a strong negative impact on the bit error rate of any modulation. So here these are the effects which have a strong negative impact on the bit error rate of any modulation. Whatever the modulation technique you use QPSK, BPSK, this will have a strong negative impact. The popular techniques, the three popular techniques are equalization, diversity, and channel coding. These are the three techniques which can be used independently or in tandem to improve received signal quality. We can use independently or combinedly, we can use these three techniques. Equalization, the first one is the equalization, compensates for intersymbol interference created by multipath within time dispersive channels. If the modulation bandwidth exceeds the coherence bandwidth of the radio channel, intersymbol interference occurs and modulation pulses are spread in time. That is what the equalization technique. An equalizer within a receiver compensates for the average range of expected channel amplitude and delay characteristics. And equalizers must be adaptive since the channel is generally unknown and time varying. Equalizers must be adaptive because the channel is generally unknown and time varying. Then the next one is diversity. Diversity is another technique used to compensate for fading channel impairments and is generally implemented, or this can be implemented by using two or more receiving antennas. Here, as with an equalizer, the quality of mobile communication link is improved without increasing the transmitted power or bandwidth. This is an important point to be noted, that without increasing the transmitted power or bandwidth, no, without increasing the transmitted power or bandwidth, the quality of mobile communication link is improved by using this diversity technique, and this can be employed at both base station mobile receiver. Spatial diversity is the most common type of diversity technique. In this spatial diversity, multiple antennas are strategically spaced and connected to a common receiving system. Here, Diversity techniques can be employed both at base station and mobile receivers, and the most common technique is the spatial diversity technique, where the multiple antennas are strategically spaced and connected to a common receiving system. One antenna sees a signal null and another antenna may see a signal peak. Right, one antenna sees a signal null and another antenna may see signal peak, and the receiver is able to select the antenna with the best signal at any time. And other types of techniques includes polarization diversity, frequency diversity, and the time diversity. CDMA systems, code division multiple access systems, often use rake receiver, which provides link improvement through time diversity. CDMA systems generally use rake receivers, which uses this time diversity technique. This is an example. Next topic is channel coding. Channel coding, which improves the communication link performance by adding redundant data bits in the transmitted message. The code message is then modulated for transmission in the wireless channel. Channel coding is used by the receiver. Mainly, channel coding is used by the receiver to detect or correct some of the errors introduced by the channel in particular sequence of message bits. There are two general types of channel codes are there: block codes, convolutional codes. Then channel coding is generally treated independently from the type of modulation used. Here, the three techniques which we discussed, the equalization, diversity, and channel coding, are used to improve radio link performance. That is to minimize the instantaneous bit error rate. But the approach, cost, complexity, and effectiveness of each technique varies widely in practical wireless communication systems. In practical wireless communication system, the approach, cost, complexity, and effectiveness of each and every technique of equalization, diversity, and channel coding varies widely. That is the point you have to note here. Then we'll move on to the next topic, fundamentals of equalization. Intersymbol interference. The fundamentals of equalization. First, we'll learn about intersymbol interference. Intersymbol interference is generally caused by multipath in band limited time dispersive channels, distorts the transmitted signal, causing bit errors at the receiver. Intersymbol interference (ISI) generally caused by multipath in band limited or frequency selective. Which distorts the transmitted signal, causing bit errors at the receiver. Intersymbol interference has been recognized as a major obstacle to high-speed data transmission over mobile radio channels. This is the major obstacle to high-speed data transmission. So what we have to do, we have to reduce this intersymbol interference. And the next, equalization. In a broad sense, the term equalization can be used to describe any signal processing operation that minimizes intersymbol interference. In a broad sense, we can define this equalization as any signal processing operation which minimizes intersymbol interference. Right. In radio channels, in wireless communication, the channels, a variety of adaptive equalizers can be used to cancel interference while providing diversity. While providing diversity, a number of adaptive equalizers can be used to cancel this intersymbol interference. So that is it. That's why this equalization is a technique used to combat ISI. Equalizers must track the time varying characteristics of the mobile channel. So these are called adaptive equalizers. Mobile fading channel is random. We know that the channel is random and time varying. So these equalizers must track time varying characteristics of the mobile channel. So those equalizers are called as adaptive equalizers. Now we'll see the operating modes of an adaptive equalizer. General operating modes of an adaptive equalizer includes training and tracking. These are the two operating modes of an adaptive equalizer: training phase and tracking phase. First one, training in the first stage. In this again we'll discuss two stages. Training first stage. The first known fixed length training sequence is sent by the transmitter so that the receiver's equalizer may average to a proper setting. A known fixed length training sequence is sent by the transmitter so that the receiver equalizer may average to a proper setting. And the training sequence is typically a pseudo random binary signal. The training signal, is typically a pseudo random binary signal or a fixed prescribed bit pattern. Immediately following this training sequence, the user data is sent. After this sending training sequence, immediately the user data is also sent, and the adaptive equalizer at the receiver utilizes a recursive algorithm to evaluate the channel and estimate filter coefficients to compensate for the channel. After sending the training sequence, then immediately the user data will be sent. Then adaptive equalizer at the receiver, generally in the receivers, adaptive equalizer is used. So adaptive equalizer at the receiver utilizes an algorithm, a recursive algorithm, to evaluate the channel and estimate the filter coefficients to compensate for the channel. The training sequence, which we have transmitted first, is designed to permit an equalizer at the receiver to acquire the proper filter coefficients in the worst possible channel conditions, so that when the training sequence is finished, the filter coefficients are near the optimal values for reception of user data. As user data are received, adaptive algorithm of equalizer tracks the changing channel. This is what the next stage, that is tracking. So here the training sequence generally designed to permit an equalizer at the receiver to acquire proper filter coefficients. That's why we have to first transmit the training sequence, because to acquire the proper filter coefficients we have to first transmit this training sequence, then user data will be sent. Then the time span over which an equalizer converges is a function of the equalizer algorithm, equalizer structure, time rate of change of multipath radio channel. Equalizers generally requires periodic retraining in order to maintain effective ISI cancellation and are commonly used in digital communication systems where user data is segmented into shorter time blocks. Generally, most of the digital communication systems uses this adaptive equalizers, and these equalizers requires periodic retraining in order to maintain effective inter-symbol interference cancellation. Then the next stage is the tracking stage. Okay, up to this clear? I think the first stage is the training stage. Second one is the tracking phase. First part we've discussed about the training phase of an adaptive equalizer. Then we will discuss about the tracking phase of. We are discussing operating modes of an adaptive equalizer. The first stage is training stage and second stage is tracking stage. Immediately following the training sequence, user data is sent. As user data are received, the adaptive algorithm of the equalizer tracks the changing channel and adjusts its filter characteristics over time. In the tracking phase, immediately after the training sequence is transmitted, user data will also sent. And this equalizers generally most commonly used in digital communication systems where user data is segmented into short time blocks. Equalizers require periodic retraining in order to maintain effective intersymbol interference cancellation. TDMA, time division multiple access, not multiplexing. Time division multiple access wireless systems are particularly well suited for equalizers. TDMA systems sends data in fixed length time blocks, and the training sequence is usually sent at the beginning of a block. Each time a new data block is received, the equalizer is retrained using the same training sequence. This is the tracking phase of this one operating mode of an adaptive equalizer. Next, we'll see the communication system with an adaptive equalizer. Next topic of operating modes of an adaptive equalizer. The next topic is communication system with an adaptive equalizer. An equalizer is usually implemented at baseband or at IF in a receiver. Since the baseband complex envelope expression can be used to represent band pass waveforms, the channel response demodulated signal and uh, and adaptive equalizer algorithms are usually simulated and implemented at baseband. Here, next slide, the block diagram of a simplified communication system using an adaptive equalizer at the receiver is shown. This is the block diagram of a communication system with an adaptive equalizer in the receiver. Now, if you see this block diagram here, x of t, if x of t is the original information signal, and here see f of t is the combined complex baseband impulse response of the transmitter channel, because here up to this is the transmitter part, this is the radio channel part, after that RF front end. X of t is the original information signal input signal. F of t is the combined complex baseband impulse response of the transmitter channel and RF or IF sections of the receiver. Then the received signal by the equalizer, or the signal received by the equalizer, can be expressed like y of t equals to x of t convolution f star of t plus nb of t. Here the equation is not given properly. This is the convolution operation, and here f star of t is a complex conjugate of f of t. F star of t, which is the complex conjugate of f of t, and this term nb of t, n suffix b of t, is the baseband noise at the input of the equalizer, and this denotes the convolution operation. If the impulse response of the equalizer is h equalizer of t, then the output of the equalizer is d cap of t, x of t convolution, f star of t convolution, h equivalence of t plus nb of t convolution, h equivalence of t. This will be the output, and when the equivalent impulse response of the equalizer is h equal of t, it means this is, then in that case the output of the equalizer is this thing. Now, to eliminate intersymbol interference, we must have this H equivalent of H equalizer of T convolution F star of T equals to delta of T, where this when it is converted into frequency domain from time domain, this is the time domain equation and this is the frequency domain equation. When we convert from time domain to frequency domain, the equation will be like this: H equalizer of F equals to 1 by F of F. An equalizer is an inverse filter of the channel. In frequency selective channel, enhances the frequency components with small amplitudes, attenuates the strong frequencies, therefore provide a flat composite received frequency response. This is about the communication system with an adaptive equalizer. Here it is very simple. This is the transmitter part and this is the channel part. Here this is the decision maker adaptive equalizer where we'll use the different equalization algorithms. Now coming to the next topic, generic adaptive equalizer. Generic adaptive equalizer. An adaptive equalizer is a time varying filter which must constantly be returned. The basic structure of an adaptive equalizer is shown in figure. Here in this is a block diagram or simply basic structure of an adaptive equalizer, generic adaptive equalizer. An adaptive equalizer, please note this point that adaptive equalizer is a time varying filter which must constantly be returned. The basic structure of this generic adaptive equalizer is shown in figure, where the subscript k is used to denote a discrete time index. Why k is there? This subscript k in these terms, it denotes the discrete time index. Here in this figure, there is a single input y suffix k at any time instant. This one, the value of this y suffix k depends upon the instantaneous state of the radio channel and specific value of the noise. The value of this yk depends upon the instantaneous state of the radio channel and the specific value of the noise, right? That means the channel and the noise which will be added and the you know this noise which will be introduced in the channel plays an important role in the performance of this generic adaptive equalizer, because we are having a single input yk. The value of this will be depends on that. Now if yk is a random process, the adaptive equalizer shown above is called a transversal filter. This structure, the adaptive equalizer structure, which is shown here, is called as a transversal filter. And this transversal filter, this generic adaptive equalizer, generally will have n delay elements. This transversal filter with n delay elements, n plus 1 taps, n plus 1 tunable complex multipliers, and n plus 1 weights. And these weights are updated continuously by the adaptive algorithm. The weights of the filter are described by their physical location in the delay line structure and have second subscript k to explicitly show they vary with time. Right. The weights of the filter, this n plus 1 weights will be there, this in this transversal filter. These weights, generally weights of these filters, are described by their physical location in the delay line structure. This is the delay line structure. These are the weight functions W0, W1, W2, so on, Wn. These are the weight functions. And these weights of the filter are generally described by their physical location in this delay line structure. And one more thing is these weights are updated continuously by the adaptive algorithms. That is also one thing you have to remember. Here, the weights are updated continuously by the adaptive algorithm, either on sample by sample or on block by block basis. Whenever k is incremented by 1, the subscript k is incremented by 1, then in that case sample by sample basis. If whenever a specified number of samples have been clocked into the equalizer, that is a block by block basis. Okay, here the weights which plays an important role in adaptive equalizer. Whatever the equalizer, you have to calculate these weights, and these weights are updated continuously by the adaptive algorithm. And this may be either on a sample by sample basis or block by block basis. How to identify sample by sample basis or block by block basis means the subscript k. If the subscript k is incremented by 1, then that is simply the sample by sample. And whenever a specified number of samples have been clocked into the equalizer, that is a block by block basis. Now, the adaptive algorithm is controlled by the error signal. Here, this adaptive equalizer, generally controlled by the error signal EK. This error signal is derived by comparing the output of the equalizer D cap K. So here, this incomplete adaptive equalizer algorithm is controlled by this error signal E suffix k, and this error signal is derived by comparing the output of the equalizer d cap of k with some signal dk, right? This is the output d cap of k, and we will compare this with the priori knowledge dk with some signal dk, which is an exact scale replica of the transmitted signal, or which represents known property of the transmitted signal. This dk, priori knowledge, simply will called as a priori knowledge dk. Will compare both the signals output and this priori knowledge to get the error signal. The adaptive algorithm uses this ek. This complete adaptive equalizer uses this ek to minimize the cost function and updates the equalizer weights in a manner that is that generally iteratively reduces the cost function. The adaptive algorithm uses this ek to minimize the cost function and updates the equalizer weights in a manner that iteratively reduces the cost function. Nothing but simply to reducing the error function. For example, LMS, least mean square algorithm, searches for the optimum or near optimum. For example, this LMS algorithm serves as a cost function here. By using LMS algorithm or RLS algorithm, which are serves as a cost functions. Here, LMS algorithm searches for the optimum or near optimum filter weights by performing the. Okay, this is example of LMS algorithm, least means square algorithm, and here this process is repeated rapidly in a programming loop while the equalizer attempts to converge. And here many techniques such as gradient steepest descent algorithms may be used to minimize the error. Upon reaching the convergence, the adaptive algorithm freezes the filter weights until the error signal exceeds an acceptable level or until a new training sequence is sent. Based on channel equalization theory, the most common cost function is mean square error MSE. MSE is simply between the desired signal and the output of the equalizer and is generally denoted by this expression expectation of E of k into E star of k complex conjugate. Here
When a replica of transmitted signal is required at the output of the equalizer, which is known as the priori, a known training sequence must be periodically transmitted. By detecting the training sequence, the adaptive algorithm in the receiver is able to compute and minimize the cost function by driving the tap weights until the next training sequence is sent. And most more recent class of adaptive algorithms are able to exploit characteristics of the transmitted signal, and they do not generally require the training sequences. Recent class of adaptive algorithms are generally able to exploit the characteristics of the transmitted signal, which does not require any kind of training sequences. These are the modern algorithms which are able to acquire equalization through property restoral technique of the transmitted signal and are called as blind algorithms. These are the most recent class of adaptive algorithms. Here, these algorithms are able to acquire equalization through a property restoral technique of the transmitted signal. These blind algorithms, generally, the blind algorithms they provide equalizer convergence without burdening the transmitter with training overhead. That is one of the advantage of this blind algorithm. Without burdening the transmitter with the training overhead, which will sent in the previous algorithm, we have seen the training sequence will be transmitted. That will be not there in this blind algorithms. And these techniques include algorithms such as CMA and SCORE. CMA is a constant modulus algorithm, and SCORE is a spectral coherence restoral algorithm. Okay. Now, this CMA is used for constant envelope on the received signal, whereas the SCORE technique exploits spectral redundancy or cyclostationary in the transmitted signal. Here, this CMA is simply used for constant envelope modulation, and this exploits SCORE exploits spectral redundancy in the transmitted signal. These are the two techniques which you'll find in blind algorithms. Blind algorithms are actually important for wireless communication, but here we'll not go into the details of this blind algorithms. Next topic is equalizers in a communication receiver. Equalizers in a communication receiver. Generally, the received signal includes channel noise. Because the noise is present, an equalizer is unable to achieve perfect performance. So there is always some residual ISI, intersymbol interference, and small tracking error. So therefore, the instantaneous combined frequency response will not always be flat, resulting in some finite prediction error. Here, equalizers in a communication receiver. In the previous section, we have seen how this generic adaptive equalizer works and defined some common notation for algorithms, design, and analysis. And now we'll see how these equalizers fit into this communication receivers. We all know that the received signal generally consists of noise. Because this noise is present, equalizer is unable to achieve perfect performance. So there is always some intersymbol interference, and here, therefore, the instantaneous combined frequency response will not always be flat, resulting in some finite prediction error. Because adaptive equalizers are implemented using a digital logic, it is most convenient to represent all time signals in discrete form only. Here, generally, these adaptive equalizers are implemented using digital logic. That's why it's a very convenient way to represent the time signals in discrete form. The mean squared error. This one, expectation of E suffix k square, is one of the most important measures of how well an equalizer works. Here, this expectation of E of ek square is the expected value, or simply the ensemble average of the squared prediction error, but time averaging can be used if E of n is ergodic. In practice, ergodicity is impossible to prove, and algorithms are developed and implemented using time averages instead of ensemble averages. So this provides to be highly effective, and in general better equalizers provide smaller values of this E of expectation of E of ek square. Minimizing the mean square error tends to reduce the bit error rate. Minimizing mean square error tends to reduce the bit error rate. For wireless communication links, it would be best to minimize the instantaneous probability of error instead of mean square error. But minimizing probability of error generally results in non-linear equations, which are much more difficult to solve in real time than linear equations. Okay, in wireless communication, it would be best to minimize the instantaneous probability of error instead of this mean square error. But minimize, but minimizing this probability of error, which results in nonlinear equations, which are much more difficult to solve in real time than the linear equations. That's why we will use this MSC. Next topic is survey of equalization techniques. Equalization techniques can be subdivided into two general categories: linear equalizers and non-linear equalizers. Equalization techniques are classified into two types: linear equalization methods, non-linear equalization methods. These categories are determined, these two general categories are determined from how the output of an adaptive equalizer is used for subsequent control or feedback of the equalizer. Right. These are classified based on the feedback or subsequent control of the equalizer. In general, analog signal is processed by the decision making device in the receiver. The decision maker determines the value of the digital data bit being received and applies a slicing or thresholding operation in order to determine the value of d of t. If d of t is not used in the feedback path to adapt the equalizer, the equalization is called as linear. Right. If the d of t is nothing but simple mm, reconstructed message data. If d of t nothing but simply the reconstructed message data is not used in the feedback path to adapt the equalizer, the equalization is linear. On the other hand, if the d of t, that is reconstructed message data, is fed back to change the subsequent output of the equalizer, then the equalization is non-linear equalizer. Many filter structures are used to implement linear and non-linear equalizers. Right. Linear equalization, the output of the decision maker is not used in the feedback path to adapt the equalizer, whereas non-linear equalization, the output of the decision maker is used in the feedback path to adapt the equalizer. Many filter structures are used to implement linear and non-linear equalizers. Further, for each structure, there are numerous algorithms used to adapt the equalizer. In that, the most common equalizer structure is a linear transversal equalizer (LTE). LT, linear transversal filter, is made up of tapped delay lines with a tapping spaced symbol period. And now we'll see the classification of equalizer, and then we'll go into the details of the common equalizer structure, LT, linear transversal equalizer. Here, the equalizers are classified into two types: linear equalizer, non-linear equalizer. Again, these linear equalizers are subclassified into two types: transversal equalizers, lattice linear equalizers. And non-linear equalizers are subclassified into decision feedback equalizers, ML, maximum likelihood symbol detector nonlinear equalizers, and MLSE, minimum least square error non-linear equalizers. Again, coming to this linear equalizer, transversal linear equalizer, again these are classified into zero forcing algorithm, LMS algorithm, RLS. These are the algorithms which are used in this equalization equalizers. These are the techniques or algorithms which are used in this transversal equalizers. Whereas in the lattice equalizer, we'll use gradient RLS. And coming to this nonlinear equalizers, transversal, again this LMS, RLS, least mean square, recursive least square, fast RLS, and square root RLS algorithms are used. And lattice, gradient RLS, and coming to this transversal channel estimation, again LMS, RLS, fast RLS, square root RLS. These are the algorithms are used in this nonlinear equalizer. This is the classification of equalizers. We will discuss this linear and non-linear adaptive equalizers in detail in coming class.